So good morning, everyone, and welcome to this first parallel session of the conference. My name is Twan Bogers. I'm an associate professor with the IT University of Copenhagen in Denmark, and it is my pleasure to chair this first session on collaborative filtering. We have 4 presentations in this session, 15 minutes each for a presentation and 5 minutes of Q&A. One of the presentations is from the industry track, and another one is from the reproducibility track. And a friendly reminder, people who like this session on collaborative filtering will probably also like the next one tomorrow at 2. Now let's move on to the first talk. So if the presenter could come up. So this first talk is called Adversarial Collaborative Filtering for Free, and it will be presented by Vivian Lai. It's work by her and her colleagues. And she will present a more efficient way of using adversarial learning to tackle the problem of noisy data in collaborative filtering.
Test. Okay. Hi. Thanks for the introduction. So I'm Vivian, and today I'll be sharing our paper titled Adversarial Collaborative Filtering for Free. And this is work done by my wonderful colleagues at Visa Research, who is unfortunately unable to be here at the conference today. So here's a brief agenda for this talk. We'll first briefly touch upon the background about adversarial collaborative filtering, and then talk about the proposed solution, and then show some experimental results to let you know that our proposed solution actually works, and then conclude the talk. So collaborative filtering is a widely used technique in recommender systems. It plays an essential role in addressing the information overload problem for users. And the main idea of collaborative filtering is that since users tend to have similar preferences, their opinions and behaviors could be utilized to make recommendations in the future. So in other words, the goal here is to predict potential item of interest based on a user's historical profile. One of the primary methods for collaborative filtering is matrix factorization. It learns the latent user and item representations by factorizing the observed interaction metrics. And then subsequently, the predicted score of an unobserved user item pair could be derived from the similarity between the user and item representations. And this is usually measured by the dot product. So in short, matrix factorization is a simple and efficient collaborative filtering method. The representations of a user and an item can be obtained via embedding lookup tables. And you can see denoted on the slide, EU and EI are the embeddings of user and item respectively. These embeddings are intended to capture and retain the initial characteristics of both items and users, which could be updated during training. So the predicted score is defined as the similarity between the user and item representations via dot product. We could then use BPR laws to train the model, and the Bayesian personalized ranking, also known as BPR, is a popular and effective pairwise method used in learning to rank for recommender system. Its goal is to optimize recommender systems towards personalized ranking, and this method is also suitable for learning from implicit feedback, where the observed interactions are often incomplete and unobserved ones are assumed to be ranked lower. While point-wise methods focus on optimizing each model prediction towards a predefined ground truth, it prioritizes maximizing the loss. So prior work has shown that models easily converge to bad optima if they are not well regularized. And in 2020 at the ICLR conference, Pierre et al. Proposes sharpness-aware minimization, also known as SAM in this, it's known as SAM, but we'll refer it to SAM in this talk, to minimize sharpness during training that could improve model generalization. SAM aims to find an optimal solution with low losses across its entire neighborhood rather than solely focusing on any single point. So in this part of the talk, we'll talk about the proposed solution a little. Generally, it can be simplified to the following equation where you minimize L theta and R theta. And R here measures the difference between the loss of the model and the loss of the model with perturbations. Loss of theta plus delta is the model perturbations, and the L2 norm of the perturbations can be bounded by phi. Mathematically, the objective function can be turned into a min-max optimization, where the inner optimization is to maximize the model with perturbation, and the outer optimization is to maximize the standard loss function. We could also alternatively update the inner maximization and outer maximization, and continually updating the model until the model converges. So sharpness-aware minimization, SAM, it adopts the gradient descent ascent framework, which requires 2 forward and backward passes on each sample in a batch. And this results in double computation time as compared to the base optimizer, and this makes it unsuitable for scaling to industry-scale data sets. So to overcome the computational bottleneck, we propose sharpness-aware collaborative filtering, also known as SharpCF, and this includes a novel trajectory loss that measures the alignment between the current and past model states. The solution combines the original loss with the trajectory loss. And as for time complexity, which it's an important thing to solve, unlike adversarial training that requires 2 forward and backward passes to alternatively update the auxiliary variable and model parameters, this solution can update model parameters by using standard stochastic gradient descent, making the time complexity of the solution similar to the original BPR model without any additional computational cost. Another pro of this solution is that it's easy to implement. So compared to original matrix factorization, we only need to conduct 2 extra steps. So firstly, for the current epoch, we will remember the loss values in the earlier epoch, and then the E would be represented by a small number like 3 or 5. And then secondly, the difference could be added between the current model states with the previous states. So this approach has a trade-off between memory and speed, since it sacrifices memory but speeds up the training process. So in this part of the talk, we'll go through some experimental results. We use 4 public data sets for evaluating the performance. And the 4 data sets are DataLens, Goala, Yelp 2018, and Amazon Book. And these data sets are, I think, commonly used in recommender task systems. So the primary goal here of this project is actually to give insights about adversarial training and acceleration on computational overhead. As a result, we only mainly compare with 2 popular baselines. The first baseline, it's BPR, which we talked about earlier on, the classic model that seeks to optimize Bayesian personalized ranking loss. And we use matrix factorization as its preference indicator. And the second baseline, it's APR, which uses the matrix factorization model and considers adversarial perturbations during training. So this slide shows the results for the data sets on 5 metrics and 3 methods. The 5 metrics are commonly used metrics too, and they are recall at 10, NDCG at 10, recall at 20, NDCG at 20, and also we measure time per epoch to gather results on the time complexity. So mainly there are 2 observations from this slide. The first observation is that while the underlying recommended model remains the same, APR and SharpCF, which is the proposed solution, outperforms BPR by leveraging adversarial training. And APR is able to achieve this by explicitly introducing worst-case perturbations, while the proposed solution implicitly smooths the learning trajectory to achieve the same effect. Both effects have the potential to smooth the loss landscape to reach the flat minima, leading to better performance. That was the first observation. The second observation is that the proposed solution has shown improvements in all comparisons, and it consistently outperforms BPR by up to 30%, with an average improvement of about 18% and a standard deviation of 7% across all data sets. So while the improvements over APR, they are not as significant as those of BPR, it still shows positive results with an average improvement of 7%. And this is presumably because SharpCF does not require us to solve the min-max minimization, which avoids the risk of getting stuck at saddle points that often exhibit large variances, as explained in the original APR paper. This slide shows the training curves for 2 metrics, recall at 10 and NDCG at 10 for all data sets. After pre-training for 200 epochs, we observed that continued training of APR and SharpCF results in significant improvement, whereas further train of BPR only leads to marginal gains. So for example, as you can see at the bottom left, in Amazon book dataset, BPR achieves a maximum recall at 10 score of around, this is very small for you to see, but it's 0.0207. And then it's further on boosted to 0.0267 by training with the proposed solution. But in short, this leads to a relative improvement by approximately 29%. This slide shows the training curves of BPR, APR, and SharpCF on all 4 data sets. And as we mentioned in the beginning of this talk, prior work has demonstrated that there is a strong correlation between the flatness of the loss landscape and the generalizability and robustness of a model. We observed that BPR has a sharper local minima in the loss landscapes as compared to APR and SharpCF across all data sets. And adversarial techniques such as APR and SharpCF, they tend to generate flatter loss. So you can see that the green line, which is the sharper loss landscape, it has a much sharper loss landscape as compared to APR and SharpCF. Overall, while APR and SharpCF achieves flat minima, SharpCF is cheaper in terms of computation. So we've come to the end of this talk, but we're going to summarize the 3 things that we talk about in this talk. Firstly, we showed that adversarial training tends to favor flat minima over sharp minima, which tends to result in better generalizability. Secondly, we proposed the sharpness-aware collaborative filtering to introduce a novel trajectory loss that measures the alignment between current and past model states. And lastly, it's able to avoid the need to solve a min-max optimization problem and enable adversarial training without adding additional computational costs. Thanks for listening to this talk. And yeah.
Thank you very much. It's time for questions. If you have questions, you can walk up to one of the microphones in the room or post them to Slido online. If there are no questions yet, then I'll start with a question. Can you say a bit more about how the size of the epoch window influences performance? You show in the paper that you use bigger and then smaller windows, right? And I think you use 3 as the default value, that the last 3 iterations. But for one of these data sets, the window size seem to keep increasing performance. So can you say a bit more about how the size of the epoch window influences performance?
Sorry, so is the question how the size of window influences performance? I think it's a little hard for me to hear from here.
I'll come closer then. So the epoch window, how does the size of that window influence performance?
So in the paper, we did show some experiments how the size of epoch affects the performance, and it gets up to a certain size, it would stabilize the performance. So I think for this part, whoever that's asking the question, it will be, you'll have a clearer idea if you look at section, I think section 5 of the paper.
Okay. No questions on Slido that I can see. Any questions in the room? Then I'll ask another question. If I go back to my notes. You showed in those, in the graphs where you showed the number of epochs that you trained it for, how performance of your sharp CF, should I come closer so you can hear what I'm saying? So if you've set the number of epochs for pre-training to 200, right? But if you set it to lower, does it take sharp CF and APR longer to improve as well? It seems like it takes them a long time to get to the point of BPR.
Sorry, session chair, could you repeat the question again? So because we set it to 200, and the answer is if we set it to longer, right? Would we see a difference in performance? Sorry, if I didn't get the question right, please feel free to come and look for me after this session. Because we set it to 200, we didn't test it after experiment results after 200 epochs. So no, we didn't see a difference in the performance.
Any questions from the audience? If not, then I'll ask one final question. We have time for that. Could you see this approach having applications beyond pure collaborative filtering? You mentioned fairness of recommendations in your future work a little bit, but could you say a bit more about where else you would like to apply this?
This is a great question, and because we are conducting research at Visa, and so we're able to use this technique in some of the research projects that we're currently doing. I'm sorry, I can't really talk about this, yeah, but.
Okay, thanks. Let's thank the speaker again. It's time for the second talk by Johan Zhao and colleagues. If I could ask you to